Hello and welcome to our Design Showcase presentation. We are Design Group 11 from the Mechanical Engineering Department, and today we will be presenting our mobile solar-powered pod.
Currently, the electrical grid in Nigeria is quite unreliable and only works about half the time. During outages, people have been using diesel gensets as well as kerosene lanterns to compensate for the lost power. These, however, are noisy, polluting, expensive, and have been linked to a variety of respiratory problems. The goal of our design was to create a portable solar-powered unit to be an alternative solution. Our design will be clean, quiet, and cost-effective. The primary function of our device is to provide power for a low-usage home in Nigeria while the power grid is down, specifically being able to provide 2.6 kilowatt hours of energy every day. We believe our device can be implemented in other warm climates, and with some adjustments even colder climates. Shown here are some of the key objectives and constraints for our design. For our objectives, we focused on exceeding the portability and convenience of the traditional genset. For our constraints, we focused on meeting portability, power capacity, and meeting safety specifications.
We designed a portable and capable solution consisting of 4 light-leaf solar panels on a base containing an inverter and lithium iron phosphate batteries. The design has mechanics similar to a cargo dolly, making it easy to tip up and roll, giving good maneuverability for the weight from the necessary electrical components and structure. The height is just under 5 feet, close to a standard cargo dolly. The width is just under 28 inches, which is the narrowest expected door opening.
The array hinges open and can be deployed attached to the base, as shown here. An alternative mounting for the array is to strap it to a sturdy structure and keep the base in a different location.
When deployed on the base, the panels can be tilted from 55 to 30 degrees to angle toward the sun. There are a total of 160 cells in the array, giving nominal power of 500 watts. Here we can see some of the linkage and supports with tubes to connect the battery to the base. The kickstand tubes insert directly into their 3D printed brackets and are pinned with clevis pins. The hinges lock with cam clamps at the ends of the hinges, similar to how a bicycle fork holds a wheel. This design allows greater solar capacity than simple panel and battery solution, while being lighter and more portable than a generator.
Our project involves the use of both mechanical and electrical design. For the electrical design, we conducted a power analysis to determine the number of solar panels and amount of battery storage that is needed. For the mechanical aspects of the design, we used hand calculations in conjunction with finite element analysis simulations for structural analysis, as seen on the right side of this slide. For our analysis of the support structure, we used a high safety factor of around 6 to add rigidity and account for the shock loading associated with going up and down stairs, as well as potential misuse, such as placing objects on top of the device. Unlike the support structure, the hinges have a much lower safety factor of 1. This is because we analyzed them in a worst-case, high-wind scenario without adding the friction force created when they are clamped shut. Because of this, the safety factor of 1 is reasonable, and it is very unlikely to experience loading higher than this case. For our power analysis, we assumed a family of 4 and sized our batteries under the assumption that a 12-hour blackout could occur without any additional generation from the sun. This resulted in 200 amp hours of battery storage. We determined the number of solar panels required after calculating the amount of generation needed to fill 200 amp hours over an average 7 hours of sunlight. This 468 watt required translates to 4 of our 125 watt panels.
Our solution considered social impacts and is designed to improve quality of life by providing a clean, quiet, and renewable form of energy. The unit itself was designed to be as safe as possible and eliminate inherent physical dangers such as sharp objects and moving parts. Environmental sustainability was considered in our design as we utilized recyclable and reusable materials such as aluminum and steel where possible. Assuming 1% of the Nigerian population adopts our solution, we will remove 4.86 million kilograms of CO2 per day from the atmosphere, which is equivalent to removing 379,130 cars per day off the road. Solar energy is clean and does not produce any waste. However, the challenge will be to properly dispose of the solar panels and batteries at the end of their 30-year lifespan. We designed our solution to be economically sustainable and affordable to a certain portion of the Nigerian population and reduce social inequality by providing power and access to basic electrical-based amenities in rural and underserved areas. Our solution will pay out in 7.5 years and provide savings of $19,500 over 25 years when compared to the diesel generators used. This concludes our presentation. Thank you for listening.